Welcome back to the Deep Dive. Today we're tackling something really fundamental. Truly basic to all science and math.
We're talking about the point. You know that concept we all learn, zero dimensions, no size, no parts.
Right, the definition from Euclid over 2,000 years ago.
Yeah.
Simple, elegant, seemed obvious.
But, as our sources suggest, that very simplicity, that zero-size idea, might be the root of a massive crisis in modern physics. It made the math look clean, sure, but reality, maybe not so much.
And that's where this deep dive heads today. We're unpacking a really bold claim coming out of South Korea, the K-Science Initiative.
That's right. They're using something called OPS one-parameter solution and an AI Buckingham machine. And the headline, they claim they've calculated the actual finite size of the point.
Finite size, that just sounds revolutionary. It undoes centuries of thinking.
It really does. If true, it could solve mysteries that have plagued physicists for decades. So our plan today. First, explore why assuming zero size caused so many problems. Then, look at this new OPS framework from 양동봉 and his team.
And finally, consider the bigger picture, what this means for science, for maybe even a Nobel Prize, and for Korea's position on the world stage.
Exactly. It touches on everything from quantum fields to national strategy.
Okay, let's dive into that first part. The curse of the zero-size point. How did something that made math so neat cause such a disaster in physics?
Well, the main disaster has a name. The infinite divergence problem, or muhande balsan-munje in Korean.
Infinite divergence. Sounds bad.
It is. If you model a fundamental particle, say an electron, as a perfect geometric point with zero size, well, the math just breaks.
Breaks how?
When you try to calculate things intrinsic to that particle, like its own magnetic energy or how it interacts in quantum field theory, the answers come out as infinity.
Infinity. That's not a physically meaningful answer.
Precisely. It's a mathematical catastrophe. It signals that your starting assumption, the zero-size point, must be wrong when applied to physical reality.
And this wasn't just a weird quantum quirk.
No, not at all. You see the same kind of problem in Einstein's general relativity. Think about black hole.
Okay, massive star collapses.
Collapses down to a point of infinite density, a singularity. Again, infinity pops up because the theory allows for essentially zero volume in both the very small and the very massive. Assuming zero size led physics into a mathematical dead end.
But physics didn't just stop there, right? They obviously found ways to keep working, making predictions. What was the fix, or as the sources call it?
That would be renormalization. It was. Well, it was an incredibly clever but ultimately unsatisfying mathematical workaround.
So what does renormalization actually do? How does it handle these infinities?
Okay, imagine you do your calculation and boom, you get infinity plus some finite number. Prenormalization essentially provides a procedure to surgically remove the infinite part and then adjust the remaining finite part so it matches the value you measure in experiments.
So you just cut out the infinity.
Sort of. It's more systematic than that. But the core idea is to isolate and discard the problematic infinite terms. The sources use some great analogies, actually.
Like what?
Like your ramen broth is way too salty, imminently salty, let's say. So you pour most of it out and add fresh water until it tastes right. Or like your cola is excessively infinitely fizzy, so you add ice to dilute it and calm it down. You get the right result in the end, but you haven't fixed the underlying issue with the original broth or cola.
But renormalization has been spectacularly successful, hasn't it? Quantum electrodynamics, QED, uses it and it predicts things to, 12 decimal places? That sounds more than just a gimmick.
And that's the crucial tension. Yes, incredibly successful predicting what happens. But physicists, even the ones who developed it, knew it was covering up a deeper problem. Richard Feynman famously called it a dippy process.
Dippy process, even Feynman.
Yes. Everyone recognized it was a temporary fix. A mathematical sleight of hand that worked beautifully, but didn't explain why the infinities were there in the first place. The success showed the overall theory was on the right track, but the need for renormalization screamed that the foundation, the zero-size point particle, was flawed.
So if the experts knew it was flawed, why stick with it for so long? Decades, right?
Well, a few compelling reasons. First, mathematical simplicity. Zero just makes equations look cleaner, more elegant. Mathematicians love that.
Okay, aesthetics count.
What else? Philosophical inertia. Western philosophy, going back to Plato, has this ideal of perfect, dimensionless forms, a point having actual size felt, messy, imperfect.
Interesting. Tradition played a role.
And probably the biggest reason, experimental limits. We simply couldn't measure anything small enough to prove the point wasn't zero-sized. The smallest scale we can probe is the Planck length, around 10 to the minus 35 meters.
Tiny, but not zero.
Exactly, but since we couldn't see anything smaller, assuming zero was the simplest, most convenient hypothesis that didn't contradict experiments. Until now, maybe.
Which brings us to this Korean research, led by 양동봉. They decided to challenge that 2,000-year-old assumption head-on. What was their approach? How did they possibly calculate a size smaller than we can measure?
They used a totally different framework. It combines this OPS one-parameter solution idea with a powerful tool called the AI Buckingham machine.
Let's break that down. OPS one-parameter solution. What's the core hypothesis there?
It's quite radical. Instead of treating fundamental constants, the speed of light, c, the gravitational constant g, Planck's constant h, even the cosmological constant lambda, as independent, unrelated numbers.
Which is how we usually think of them, right? Just fundamental values we measure.
Right. OPS proposes they aren't independent at all. They're actually interconnected, part of a single underlying structural order. And this entire order is governed by just one fundamental parameter.
Wow. So not 4 or 5 separate universal constants, but one system.
That's the claim. And the AI Buckingham machine is the engine they use to explore this. It employs sophisticated AI, leveraging something called the Buckingham pi theorem.
Buckingham pi. Sounds familiar from engineering, maybe?
Yeah.
Deals with dimensions.
Exactly. The key is that the AI analyzes the relationships between these constants using dimensionless numbers, danwi unknown su, numbers without units like meters, kilograms, or seconds.
Why is dropping the units so critical?
Because units like meters or seconds are human inventions, right? They depend on history, convention. Dimensionless numbers strip all that away. They represent pure, universal relationships between physical quantities. It forces the AI to find the inherent structure, the universe's own language, free from our historical baggage.
Okay, so using this universal, unitless language, driven by the idea of a single underlying order, they calculated the size of the point.
Yes. The OPS framework, analyzed by the AI Buckingham machine using dimensionless constants, led directly to a calculation confirming the point must have a finite non-zero size.
And the number. What did they find? This is the core of the claim.
The numbers are staggering, almost impossible to grasp. They calculated a characteristic length for the point of roughly 10 to the minus 95 meters.
Whoa, okay, wait. 1095 meters. The Planck length, our measurement limit, is 1035 meters. That's 60 orders of magnitude smaller.
Precisely. And a corresponding minimal mass around 134 kilograms and a minimal time duration of about 104 seconds. These define, according to the theory, the absolute smallest possible unit of existence.
But I have to push back a bit here. If it's 1095 meters, something so incredibly far beyond anything we could ever hope to measure, how is that functionally different from zero? Isn't it just replacing one unprovable concept with another slightly larger than zero, but still unprovable concept?
That is the absolute key distinction, and it's not just philosophical. Zero is mathematically different from any finite number, no matter how small.
How so, in practical terms for physics?
Because a zero-size point allows for infinite concentration of energy or charge. That's the source of the divergence problem. A point with a size of 1095 meters, however small, still has a non-zero volume. Energy and charge density can become enormously large, but they remain finite.
Ah, so mathematically infinity is gone.
Exactly. You replace a singularity, a point of true breakdown, with an extremely dense but physically describable structure. It establishes a fundamental granularity to space-time itself. The infinities that required renormalization just evaporate.
Okay, that's huge. So the immediate consequence is solving the infinite divergence problem.
Correct. If the point isn't zero-sized, the root cause of those infinities vanishes.
Which means no more need for renormalization.
Precisely. That whole dippy process, the mathematical gimmick, becomes unnecessary. This offers a fundamental solution to the problems in quantum field theory, not just an effective workaround. It addresses the why behind the infinities.
And what about the other big problem area, general relativity and singularities?
This finite point size offers a direct resolution to the singularity problem too. Black hole centers, the Big Bang origin. They are no longer points of infinite density where physics breaks down.
So they become, what, just incredibly dense regions?
Yes, regions with the calculated minimal size and enormous but finite density. This provides a natural bridge between quantum mechanics and gravity, potentially paving the way for a true theory of quantum gravity, because you've removed the infinite barrier between them.
The implications just keep expanding. This doesn't just fix physics equations. It seems to challenge the very foundations of mathematics and even philosophy, overturning Euclid after 2,000 years.
It certainly does. Mathematically, the definition of a point has to change. It's not that which has no part, but perhaps the fundamental unit possessing minimum size.
That could even affect how we think about continuity, right? Like the real number line.
Potentially, yes. It suggests that maybe even space and numbers aren't perfectly smooth and continuous, but are built on an incredibly fine grid of these minimal point units. It could have ripples through set theory, topology.
And philosophically, you mentioned nothingness and something.
Right. It reframes that ancient dichotomy. If the absolute minimum, the point, isn't true nothingness, zero size, but is the smallest possible something, finite size, then the boundary between existence and non-existence isn't an absolute void. It's this minimal, calculable structure.
That's quite profound. It almost sounds like it connects to creation myths.
The sources suggest that connection. Concepts like the point of creation, or techo in some traditions, could be seen as resonant with this idea of the Big Bang originating not from an infinitely dense mathematical singularity, but from a specific finite physical structure, the minimal point unit.
Okay, let's shift gears to the bigger stage.
Yeah.
This isn't just academic. It's presented as the K-Science Declaration. What's the significance for South Korea itself?
It signals a major ambition, a paradigm shift. Historically, South Korea has excelled as a technology follower, Jisol Chigyagokok, brilliant at adopting, adapting, and perfecting existing global knowledge thanks semiconductors, AI implementation.
Right, a manufacturing implementation powerhouse.
But this discovery, if validated, positions Korea as a potential knowledge rule setter, Jilseo Zedguk. The nations that define the fundamental rules of science, like Britain after Newton or the US after Einstein, tend to lead globally, not just scientifically, but economically and culturally.
And this ties into current political visions as well.
Yes, the sources explicitly connect this to President Lee Jae-myung's vision of a stronger Republic of Korea, Daeogahan Daehanminguk. Science, particularly foundational science like this, becomes a pillar of national strength, diplomacy, and identity.
Creating a K-Science brand, maybe, alongside K-pop, K-drama.
Exactly. It's about national pride and legacy. The idea is that future textbooks might state, Korea was the first nation to calculate the finite size of the point. That's a powerful narrative.
Let's talk about the ultimate scientific validation, the Nobel Prize, and also brass tacks, investor interest.
Yeah.
Is there real economic potential here?
On the Nobel front, you can see the argument. It potentially modifies a definition accepted for millennia. It claims to solve fundamental, long-standing problems like divergence and singularities, and it introduces a potentially universal new language for physics through OPS and dimensionless analysis. These are the hallmarks of Nobel-worthy breakthroughs.
The potential is clearly there. But investors, how do you pitch the industrial value of 1095 meters?
The value isn't in making things that small. It's in the framework OPS. Having a more fundamental, unitless understanding of how physical constants relate could optimize complex modeling. Think AI algorithms trained on more fundamental physics, or designing next-generation semiconductors where quantum effects at near fundamental scales matter.
So it's about the underlying theory enabling better design tools.
Partly, yes. And crucially for investors, there's the intellectual property aspect. The researchers are using something called zero-knowledge proofs. ZKP.
Zero-knowledge proof sounds intriguing. What does that do?
It's a cryptographic technique. It allows the researchers to prove to anyone, other scientists, investors, that their calculation result, the finite point size derived from constants, is mathematically correct without revealing the core proprietary algorithm or the exact OPS structure they used to find it.
Ah, so you can verify the answers right without them giving away the secret sauce.
Exactly. You protect the valuable IP while still allowing for transparent verification of the outcome. That's incredibly attractive for securing investment in foundational research with potentially huge long-term value.
This has been quite the journey, from Euclid's simple zero-size point that ultimately broke physics, to this potential new era defined by a calculable, finite minimum size pioneered by K-science.
It really represents a potential paradigm shift, moving from an assumed problematic zero to a calculated, problem-solving finite value. It underscores how sometimes the most obvious assumptions can be the biggest roadblocks to progress.
Challenging that obvious truth seems key.
Absolutely. Giving the point structure, even at an unimaginably small scale, seems to unlock solutions to some of science's most stubborn puzzles.
It leaves you wondering, though, if the point itself, the absolute minimum unit of existence, has this intricate structure derived from universal constants, what does that imply about the complexity hidden in the supposedly empty space between the points? If the ultimate constituents aren't simple, maybe the void isn't so void after all.
That's certainly a fascinating thought to carry away. What is the structure of nothing?
Indeed. Thank you for joining us for this deep dive.